Hi everyone, my name is Janhavi and this is my individual lab 2 based on the motion of a falling object. In this lab, I will be analyzing the motion of an object that's dropped from rest and falls somewhat slowly straight down. I'll be doing this using Tracker. We'll then observe the effects of gravity and drag on the object and their role in changing the object's velocity. I'll then construct two computational models. One will consider only gravity and the other will take into consideration both gravity and the drag force. After this, we'll compare my observed versus predicted position graphs using the experimental and computational data, make some observations on that, and then I'll answer some key questions for this lab. So here are some of the key concepts that this lab focuses on. When an object is dropped from rest, the only forces acting on it are the forces due to gravity and the drag force. These two forces act in opposite directions and don't cancel each other out, resulting in a downward net force, which then results in an acceleration in the downward direction. Here are some of the key formulas that I used in my lab. I'll be using these in the computational model to predict the object's position and velocity as a function of time. Over here, you can see the velocity update formula. This calculates final velocity given initial velocity, net force, mass, and change in time. The position update formula calculates the final position given initial position, average velocity, and change in time. The drag force is equal to the square of the instantaneous velocity of the object multiplied by b, which is the proportionality constant of the drag force. And the force due to gravity is the object's mass multiplied by acceleration due to gravity, which in this case is 9.81 meters per second squared. So here's my analysis on Tracker of the motion of a falling object, which in my case for the lab was the cap of a glue stick. And here's the position versus time graph that I obtained using my analysis on Tracker, which we'll soon compare with the computational data that I'll obtain from GlowScript. Here's my GlowScript code, which I started by using the starter code provided by the lab. This first slide is my code for the computational prediction that considers only the force of gravity. B, in this case, is equal to 0. This is because this model is only considering gravity and there is no air resistance, hence there is no constant for the magnitude of the drag force as it doesn't exist. You can see that I applied the velocity update formula over here and the position update formula over here. Since there's no drag, I set net force equal to the weight of the object. This next slide now shows my GlowScript code for the computational prediction that considers both the force of gravity and the drag force. In this code, my value for B is set to 0.0001, which I obtained through trial and error, as this resulted with my final position to be the same as my experimental data. You can see that I also applied the velocity update and position update formulas. Another key difference is the net force, which now includes both the weight of the object, which is the force due to gravity, and the drag force. So this graph here shows the position versus time graph for all three situations of data. The blue line shows my experimental data from Tracker, the red line shows my computational data that only considers gravity, and the yellow line shows my computational data that considers both drag force and gravity. So as you can see, this red line over here, which is the computational model with only gravity, deviates from the computational model with drag plus gravity and my experimental data as time increases. This is because in reality, the drag force does exist. Hence, the computational model that only considers gravity predicts my object to travel further than reality due to the drag force not being included. The computational model graph with both gravity and drag is almost the same as the graph with my experimental data. This is because it takes the drag force into consideration, which makes the data much more accurate as it resembles reality more. To improve analysis of data, I think it's very important to better understand drag force and other factors that might affect the object as it falls. So those were some of my observations from this lab, and now I'll answer some key questions. So which, if any, of my models predicted a terminal velocity? A terminal velocity is reached when the drag force is equal and opposite to the weight force of the object. So this means that the drag force would have had to be considered if one of my models had predicted terminal velocity. This can be seen in the computational model that took into consideration both drag force and gravity. And we may possibly see terminal velocity being reached as the graph line starts to flatten out and become a straight line. The next question is to imagine that the object was initially thrown downwards, and then think about whether the terminal velocity in this case would be the same or different from the case where the same object was initially dropped from rest. Well, the terminal velocity is affected by the velocity needed for the drag force to be equal to the object's weight. If the object was thrown downwards, it would change the initial velocity, but the terminal velocity for an object is specific to the object itself, and hence won't be affected even if the initial velocity was changed. Thank you.